Now let's talk about scale diagrams. I've got a question here. It says the diagram shows a particle tracks in a detector. Positive pion decays into an anti-muon at point X. And then they've given us the initial path of muon is at an angle of 18 degrees to the direction of the pion as shown. They've given us the data as well here for all the momentum of the pion, muon, and neutrino. And this will deduce whether this data is consistent with the law of conservation of momentum. Okay, so we're going to be answering this question. Remember, this is the most important part of this question. All right, and they tell us how we should solve this question by using a scale vector diagram. Okay, so this is how the situation should look like. You have the pion, and it decays into muon and neutrino. Muon with the mu, neutrino I've shown with the n, and pion with the pi. So the momentum of pion should be equals to the momentum of the muon plus the momentum of the neutrino. This is a vector equation, so which means these are the components. These are the, and this is the resultant. Okay, so when we draw a triangle, the momentum of the muon and neutrino will give you the resultant momentum of the pion. So I hope that's clear. It's not just simply adding them up. It shows you the vector equation in the triangle. Okay. And how do we get that equation? We get it from using conservation of momentum. So total initial momentum is total final momentum. Total initial momentum we can say is the momentum of pion. Total final momentum is the momentum of muon plus the momentum of neutron. We get an equation like this. Again, this is not just simply adding them up and seeing if both are equal. It's more specific. We're talking about a vector equation. So this is a vector equation where we see these two are the components and this is the resultant. So when we draw a triangle, we have got components and resultant. That's exactly what this is showing. And it's basically the same thing here as well. Okay. So these are vector equations. Keep that in mind. And this equation will help us with the rest of the question. Okay. So keep that in mind. The momentum of muon and neutrino are going to be components and pion is the resultant. Now, what I'm going to do is I'm going to draw a vector triangle. So I've got the same situation here. And now what I'm going to do is I'm going to pull this vector line back. Okay, so I'm going to pull it back like this. The reason I'm doing this is so I can draw everything in the correct orientation. Okay, so I'm going to pull that vector back like that. And I'm going to get this angle as 18 and this also as 18. Both of them are 18 because they're vertically opposite angle. Okay, I've pulled it back now. And keep in mind, this is the resultant. This is the component. Okay, and now what I can see here is that, let me just extend this a bit. Okay, we need another component here as well. And that's going to be like this. And basically that component here is basically the momentum of the neutrino. So the momentum of neutrino, the momentum of muon, the momentum of the pion, right? Now you can see the vector equation makes sense. Momentum of neutrino plus the momentum of muon is equal to the momentum of pion. Momentum of a neutrino plus the momentum of muon gives the resultant momentum, the momentum of the pion. So I hope that's clear. Okay, the reason I took a bit more unorthodox approach to this question is because it's a bit different. It's a bit unique question. So we went a little bit of a different route than we usually do. So yeah. All right. Now what we can do is we got this triangle now, and remember we've got this dot. This dot will help us a lot. So keep in mind this is our reference point here. This dot. So everything is going to be starting from this dot. Now remember, to place your dot, always place it in the place where we have the most information. Okay, so it helps us in drawing. Let's say you put the dot here. We don't know the angle, and that's going to be a bit difficult. We do know these two sides. We know all the sides actually, but we gotta go where the most information is at, and that's here because we know the angle. All right. Okay. Now what we can do is we can choose our scales. Good scales for this is going to be 1 centimeter is equals to 0.1 times 10 to the power of minus 19 kg meter per second. And when you apply the scales, you get the momentum of pion as 12 centimeter, momentum of muon 7.5 centimeter, and momentum of neutrino as 5.4 centimeter. Okay, then remember our dot. This is our dot. And then from the dot, I'm going to draw a line like this, which is going to be showing the momentum of pion, and that line will be 12 centimeter. So that line will be 12 centimeter. So I draw that line, 12 centimeter here. And then remember the angle. So I'm going to get an 18-degree angle. And then I'm going to draw the momentum of mu1. Then we measure an angle till 18 right over here. And I draw till 7.5 centimeter line. Okay. And then remember, let's go back. Okay, we're going towards the dot in both of these cases. So I'm going to draw the arrows towards, like this, like this, like this, like this, going towards that point. Okay, so they're going towards the dot. That's why it's very important to understand that as well. Okay, after that, I'm going to join together and I'm going to draw all the arrows properly. I'm going to label each of them as momentum of pion, mu1, and neutrino. If you don't do this, I can't guarantee you will get the marks from the mark scheme. Okay, and I also measure the momentum of the neutrino as well, and I'm getting the same thing that they gave me in the question. I measure 5.4. I change it back. I get 0.54 times 10 to the power of minus 19 Newton second. Okay. And then this is going to be my final triangle. That's how it's going to be looking like. Very beautiful. We got the two components there. We got the resultant. Everything is nice. And then very important, write your conclusion down. The conclusion is, as the three lines of the vector triangle are in correct orientation and direction, they form a closed triangle and hence the momentum is conserved. Okay, basically everything matches up how it's supposed to. You've got the components and resultant, hence the momentum is conserved. Okay. Just one more point and then we'll end this. So the momentum of neutrino and mu1 is equal to the momentum of pion. That's very important because initially when we talk about the initial situation, what's happening initially? We have only got the momentum of the pion. That's it. There's nothing else. After, what happens is that we got the momentum of mu1 plus the momentum of neutrino. Now this is all we're speaking about in terms of vectors here, okay? So we've got this after the decay. Okay, after the decay, we've got this. So both of these, when you find the resultant of them, it's equals to momentum of pion. That's nice because initially we've got the momentum of pion, and then finally we've got two momentums. But when you find the resultant, it's just equal to the momentum of pion again, which means initial and final momentum are the same. Momentum is conserved. Hope that makes sense.